right, so we've got 2 kilograms of air in a piston cylinder assembly. It undergoes 2 processes. Tells me I can assume the gas behaves as an ideal gas, so I went ahead and put that in my assumptions. And if I look at my givens, let's kind of walk through the problem statement and see how we got our givens. So it's 2 kilograms of mass, it's a closed system. Mass is the same at state 1, state 2, and state 3. Initially, at state 1, the pressure is 500 kilopascals or 0.5 megapascals and 227 degrees Celsius, which I have converted to Kelvin, absolute temperature units. It then undergoes a constant temperature process, so an isothermal process, until the volume is twice its initial volume. So at state 2, V2 is twice what V1 is, and the temperature T1 and T2 are equal to one another. Next, it undergoes a constant volume process from state 2 to state 3, so V2 and V3 are equal to one another, to a final pressure of 500 kilopascals or 0.5 megapascals. Now, because it says that I can assume it's an ideal gas, I really don't need to verify that assumption, but sometimes I might ask on a test or a homework problem, was that assumption an okay assumption to make? And so what you need to do is just check and see if one of those 3 conditions has been met. That the Z value, the generalized compressibility factor, is greater than 0.9, the reduced temperature is greater than 2, or the reduced pressure is less than 0.1. And if just one of those conditions is met, you can make the assumption that it's an ideal gas. I noticed at state 1 and 2, it's an isothermal process, the temperature is the same, so I'm going to calculate the reduced temperature at state 1 and state 2, and I see right away that it's greater than 2. So that critical temperature is a value that I can pull off table A1 for air, and once again, I get that the reduced temperature is greater than 2. Then state 3, I don't know the temperature, but I do know the pressure, so I can calculate the reduced pressure. I get that critical pressure off of table A1, and I can see that my reduced pressure is less than 0.1. So I verified that it's an okay assumption, it's a good assumption to make, that this air behaves as an ideal gas for state 1, state 2, and state 3. Now I'm ready to find P2. Since I've just proved that assuming it's an ideal gas will lead to minimal error, let's put it that way, I'm going to go ahead and use that ideal gas law. So P2V2 over MRT2 is equal to 1. Well, unfortunately, I've got one equation and I've got 2 unknowns, right? I don't know the pressure and I don't know the volume. But I also note that at state 1, this is also true, right? I can apply the ideal gas law at state 1, and since both of these quantities are equal to 1, they're also equal to one another. And the reason that this is helpful is because I can cancel some of the things out. Mass is the same on both sides, the specific gas constant is the same on both sides, and the temperature is the same on both sides. So I cancel things out and I get this nice simplified equation for P2. I don't know V1 over V2, but I do know the relationship between them. And so I just plug things in and I see that P2 is 250 kilopascals. Now I move on to T3. I apply my ideal gas law at state 3, but once again, I'm left with this scenario that I've got one equation and I've got 2 unknowns. I don't know the volume at 3, and then I don't know the temperature at 3. But I'm going to do a similar thing as I did in part A. I'm going to apply the ideal gas law at state 2, and because both of these quantities are equal to 1, they're equal to one another. I'm going to cancel out the mass and the specific gas constant as well as the volume, because the volume is the same from 2 to 3, and I get a nice simplified equation for state 3. And as long as that temperature is in terms of absolute temperature units, in this case, since I'm in SI units, it's going to be in Kelvin, then I can solve for T3. Then finally, I need to get the total work, and that's a capital W. It's in kilojoules, not kilojoules per kilogram, so capital W. And this would be the work for between states 1 and 2, process 1, and state 2 to 3, which is process 2. So you'll notice that between 2 and 3, it's a constant volume process. You don't have any expansion or compression. You have no boundary work, and there's no indication that there's any other type of work going on. So the only work that I really have to worry about is from state 1 to state 2. And I do have boundary work because I do have an expansion process from state 1 to state 2 since the volume increases. So what I'm going to do is I'm going to apply the equation for quasi-equilibrium boundary work. So all this means is that any expansion is happening slowly enough so that it can be modeled as quasi-equilibrium. So I've got the integral of P dV. Well, the pressure is not constant, so that can't come out of the integral, but I can get an equation for pressure as a function of volume so that I can integrate this equation here. And if I look at the terms there, the mass, the specific gas constant, and the temperature from 1 to 2 is constant. So those are going to come out of the integral, and I'm left with the integral of 1 over v dv, which is just the natural log of v2 over v1. So if I calculate, I also can calculate the specific gas constant. I don't think I've actually shown that here yet, but that specific gas constant is R bar over the molar mass. R bar is the universal gas constant. Molar mass is the molar mass of air, which you can look up in table A1, and just make sure that that temperature is in absolute temperature units, and I can solve for the total amount of work, 198.9 kilojoules. Well, I hope that was helpful. Thank you for watching, and let me know if you have any questions.